Urban adaptation. From the perspective of engineering program management and critical infrastructure analysis, the presence of wildlife in high-density urban centres should not be seen as a mere biological anecdote, but rather as a process of system optimization. Coyotes in Los Angeles and wild boar in Barcelona are operating under a navigation logic that any network analyst would recognize. They are identifying and exploiting vulnerabilities and paths of least resistance in the design of our cities. These animals have executed what we could technically call a biological hack of the infrastructure. They have decoded traffic light cycles, urban surveillance blind spots, and the topology of drainage tunnels to establish logistical survival networks. As engineers, this compels us to rethink the concept of the urban infrastructure user. We no longer design solely for humans and their vehicles. We are designing for a technical ecosystem where fauna is an active participant. The technical feasibility of integrating biological corridors into current smart cities fundamentally depends on our ability to model variables previously considered as noise. The design of a modern smart city must now incorporate stochastic simulation models that predict animal movement based on resource availability and risk mitigation. These models integrate real-time vehicular flow with motion sensors and ambient acoustics. For a biological corridor to be functional, forensic engineering teaches us that acoustic and light isolation is vital. If engine noise exceeds certain frequency thresholds, or if LED lighting is too intrusive in the blue spectrum, the corridor becomes inoperative, regardless of its structural quality. This is where precision engineering comes in. We need luminaires with dynamic spectrum control that automatically adjust when thermal sensors detect the passage of key species, reducing light pollution without compromising public safety. Drainage infrastructure and bridges can no longer be seen as isolated assets. Their preventive maintenance must now consider the integrity of these migratory routes. We are talking about a transition from a purely anthropocentric design to a technical ecosystem approach. The implementation of IoT sensors in sewers and underpasses allows monitoring not only water flow, but also the frequency of biological transit, enabling dynamic adjustments in surface traffic management to avoid collisions. From an operational standpoint, this approach enhances the city's resilience. Infrastructure capable of coexisting with local biology tends to be more flexible and less prone to catastrophic failures due to lack of environmental adaptation. My analysis as a mentor and program manager is clear. Integration is not just an ethical issue, it is a matter of systemic efficiency. Urban fauna is using our transport networks as a physical communication protocol, and our responsibility is to ensure that smart city architecture is robust and versatile enough to support this unexpected but inevitable traffic. Ultimately, the adaptability of smart cities will be measured by their ability to process biological complexity as just another data point in the design matrix. We are transforming urban centres into nodes of technical biodiversity, where practical functionality and system reliability are maintained through an architecture that respects and utilises natural patterns to strengthen the urban fabric.